Tim DelSole, who's going to present, does the multi-model ensemble enhance skill?
All right. First, I wanted to thank the organizers for inviting me to present this. I appreciate the opportunity. And this is work I've done in collaboration with Michael Tippett and Jyoti Natala. So this is a special session on NMME, so I'm going to assume you're all familiar with NMME. I'm not going to review that. This is the latest plume from the NMME. The solid black line is showing the observations as a function of time, and this is NINA 3.4 on the vertical axis. And then the colored lines are showing forecasts from different models, and the black dotted line is showing the multi-model mean, and then the solid colored lines is showing the ensemble mean from individual models. And what you see is many of the ensemble means are close to the multi-model mean. So a question that arises a lot with this kind of study is the multi-model mean significantly better than just an individual model? This is an important question for the NMME because there's a lot of resources that go into constructing the NMME, and if you can't show that your multi-model skill is significantly better than just this individual model, that would raise questions about where you should devote those resources. Should it be in the multi-model mean or multi-model, or should it be in the individual model? So the question I'm going to address is the skill of a combined forecast significantly higher than that of a single forecast? And what are some approaches to doing that? And one is just to compare mean square error. So this is a figure I've taken from Kirtman et al., which explains the NMME. What is shown here is the root mean square error over a particular area where September starts for certain lead times and over a certain period. And the horizontal axis is showing the multi-model mean error, and then the vertical axis is showing a particular model. And then the thick black diagonal line is just the 45-degree line. So all the points that lie above the horizontal, this diagonal line, correspond to cases where the individual model has more error than the multi-model mean. This percentage is the number of points that lie below it. So that this 36% means it's the number of times the individual model had less error than the multi-model. And so the question is 36% significant? Can we conclude from that yes, indeed, the multi-model mean is significantly better? And we may also want to dissect that question even further and ask, are there certain lead times or target months where there's an individual model is better or worse than the multi-model mean? So this is only a 12-minute talk, so I don't have time to defend all my assertions. So I'm just going to make an assertion here, and that is a rigorous test for the difference in mean square errors does not exist when the mean square errors are calculated from the same verification data and the prediction models are not nested. So what I mean by that is when you're comparing two quantities, virtually every statistical test that you know when you're comparing two quantities assume that those two quantities are derived from independent data. However, in this study and in any kind of multi-model study where you're comparing models, you're looking at the same verification data to evaluate your mean square error. So you're evaluating the mean square error for two models, but you're using the same verification data. And so you can't assume that your mean square errors are independent. In fact, you can prove they can't be independent. So the result, we can't really take the usual kind of test to decide if the two mean square errors are significantly different or not, except when the prediction models are nested. And what I mean by that is if you're considering two models, one model can be obtained from the other by choosing the parameters of that model selectively. But in the NMME, what we have are dynamical models. And we don't construct them in a way so that one dynamical model can be recovered from another dynamical model by changing the parameters. So that nested approach doesn't work in this case. However, I will use this nested approach to actually answer the question. A corollary of this is that you can't attach confidence intervals to mean square error to do a rigorous test of whether two mean square errors are different. I'm aware that in the literature, people do this, and I'm saying that you cannot do this. And so if you disagree with me, I would like to know that before I publish this paper. So how am I going to do this? So let me try to explain exactly how I'm going to go about answering this question. In this case, I'm going to let O represent observations, F represent forecast, and C represent your combination of forecasts, excluding the model that you're interested in comparing. So at this point, I'm assuming that you have some procedure for combining the models. It could be an average, it could be a regression, it could be a ridge regression. I'm assuming that you've already got some method for combining models, and the parameters that are involved in that combination have been estimated from a separate data set than the one we're going to use to address this particular question. And so the skill of just the single forecast can be measured by the correlation. So this symbol here represents correlation between observations and forecasts. And then the skill of the best linear combination of these two forecasts can also be measured by correlation. But we're going to use the multiple correlation, which is really the correlation between observations and a linear combination of the two forecasts where you choose the parameters to maximize the correlation. So we call that the multiple correlation. And so the basic question we're asking is this multiple correlation larger than just the correlation of a single model? So I've just repeated those definitions up here. I've modified slightly. It's exactly equivalent. I'm asking if the correlation between observations and some scaled version of the forecast, what its value is. And as you know, when you scale something in correlation, it doesn't care. Correlation doesn't care if you rescale the variables. The reason I'm doing that is to draw the parallel with this multiple correlation. And now in general, when you want to know in statistics if two things are different, what you do is you formulate the null hypothesis and say they're not different and try to disprove that. And so in this case, what we're trying to do is address the hypothesis, are these two correlations equal? And you can see now from the mathematics, the way I set it up, is that when these two are equal, it's exactly when this coefficient in front of the combined forecast is 0. So now that's a standard linear hypothesis test in linear regression. And so we know how to do that test. So to test this hypothesis, that parameter is 0, we know it ends up being a t-statistic, where the top part is the least squares estimate of that coefficient, and you divide it by some standard error of that estimate. And it can be shown that this t, when you square it, it is equal to the difference between the squared correlation of this multiple correlation minus the correlation of the individual model. And the bottom part, 1 minus r squared, is the total unexplained variance by any of the models. So what you have is, what this shows is you're clearly comparing two correlation skills. And so there's a formal test for whether that difference is high enough for you to say that there's a significant difference. And finally, you can also show that it's exactly equal to the sum square error of these two models. So that also clearly shows that we're comparing errors. So whether you measure your skill by mean square error or by correlation, we're answering the same question about whether those two measures are significantly different or not. And then one last thing to point out is that in interpretation, if you have a significant t-value, you can say that if you were to take your forecast and regress it out of your combination, then the residual still has skill. So this is an important point because, for instance, suppose all your skill comes from one thing, such as Nino 3.4. So if you already have a forecast that's capturing Nino 3.4, then when you regress that out of the combined, you have no more skill left. So the only way to get this high t-value is you have to be predicting something that's different than the forecast that you actually have. Okay, so I assume that you had to have some kind of combined forecast, and in this, just for concreteness, what I'm going to assume is I'm going to choose weights that are equal. And there have been numerous papers to show that just equal weighting is very competitive and often the best way to combine the forecast, so I'm not losing anything by assuming equal weighting. And then for the NMME, the basic message of this slide is I'm going to use 10 ensemble members from all the models, except for COLA, which only had 6. But I don't think any of those details matter. All right, so this is the main result of this study. What I'm showing here is the t-value as a function of the target month on the horizontal axis. It goes from December to December. And as a function of the lead month, which is the vertical axis. And the color coding is such that where there's color, it's significant, the t-value is significant. And everywhere where it's white, it's insignificant. All right, and remember, the t-value tells you that given relative to a single model, by including it with the multi-model mean of the other models, you enhance the skill. So the fact that all these panels for all the different models all have color tells you that by adding a multi-model mean to your individual forecast, you significantly enhance the skill. Another way of saying that is no model can claim to be so good that they can't be improved by combining with some other model. I don't have time to really dissect this figure too much. Some highlights is that the Canadian models have the most white space, so they're the ones that are least hurt by by the combination or by not having a multi-model mean. For the CFSV2, you see the deep red. That indicates that during the winter, it has helped a lot by combining it with other models, and also in the first few lead times in the fall. And in CFSV1, you see it significantly helps in the first few months of all the target months, and in particular during the spring area, which has been known as the spring barrier. So let me look at that a little bit more closely. What I'm showing here is the correlation skill in the same format. Horizontal axis is showing the target month. Vertical axis is showing the lead month. And the transition from red to blue corresponds to a 60% correlation, and then white means it's insignificant. And so again, with the CFSV1, what you see is this white gap, and so that's the sort of a well-known spring barrier. And so a reasonable thought of what this t-value or this t-test is doing is whenever a model has almost no skill and other models have skill, then it makes sense that when you combine them, you would have an enhanced skill. So from that kind of argument, you would expect some kind of inverse relationship between the t-value and the correlation. Whenever the correlation skill of that model is low, then you might expect it might be helped by adding it with other models, and so you have a high t-value. So this is showing a scatter plot to check this idea. Scatter plot of correlation on the horizontal axis and the t-value on the vertical, and you do see, and there are some models that have this inverse t relationship. So whenever the models become not so skillful, they're actually helped by including with other models. However, you can see other models do not have that relationship. The COLA model and the GFDL model don't seem to show that. And in fact, the CFSV2 shows the opposite relation. Whenever the model is showing the most skill, then it's also most benefited by combining with other models. So let me end there. Two main points. I proposed an objective procedure for deciding if the skill of a combined forecast is significantly higher than a single forecast. And skill of each model in the NMME is significantly enhanced by combining it with other models, at least for some lead times and target months. And just before I came in here, someone was telling me that because the title of my talk was a question, they could anticipate the answer had to be no. So I'm actually bucking that trend, and so I'm actually saying yes to this question. So let me end there. Thank you.
Excellent time, lots of time for questions. I see one in the back. So Newman can jump, but I can run.
Thank you. So I think this is really great work. I was wondering if you have thought about how you would test to see whether the big advantage of having probabilistic forecasts from the ensemble and how you would compare that to the individual models.
Yeah, so it turns out that a lot of this, what I've talked about, can be derived from a probabilistic framework. So I've been doing some work with scores, proper local scores, and it turns out that with that analysis, which is the way I actually started, you end up with a very similar analysis, assuming everything is Gaussian. So when it's non-Gaussian, I don't exactly know how to modify that yet, but I think there's a framework available for that.
Hi, Tim. You must assume that all these models should more or less have the same skill. If you have a very good model, the other is poor, then your conclusion may be no.
Yeah, so you could play all kinds. So one thing I forgot to mention is that there's no unique way to address this question. So the way I approached it is I took the mean of all the other models. But you could play games of this sort of asking, well, what if you combine it with just one model or two other models? And in particular, you notice that the Canadian models were the ones that were sort of least helped by combining. But that could be because when I did the multi-model mean, there was another Canadian model in that mean, and maybe they were sort of sharing information there. So there's a lot of issues about when you combine them, can you use this to sort of tease out what the models are actually doing?
Yeah, I have another question. You said for CFS version 2, including other model, actually when the model have a high skill, you have a higher T. That's yeah, right. That's a little bit hard to understand. I wonder if you can try to use the root mean square error to repeat analysis to see if that can give you slight difference? It's a little bit hard to understand that.
So I have two responses to that. I would claim that the significance test doesn't matter whether you're looking at mean square error or correlation. I would argue that in both cases, I can write my t-value as a difference of errors or a difference in correlations. In terms of explaining this, I agree it is a little perplexing to explain this, but remember, I think what might be going on here is this concept of complementary skill. Remember, you can only get a large t-value if the model you're combining it with, after you regress out the forecast that you're looking at, there has to be some skill left over. So in other words, there has to be more than one thing that's being predicted that has skill. And so I think what's going on in CFSV2 is predicting its own thing, and whatever that is, the other models are not predicting it. So even though it has a high skill, it's high skill on some component of predictability, and then the other models are predicting something else, and so when you combine it, you get even more predictability.
Last question, Peitel.
Okay, my question is, a single model has less members, but combine the other models, a lot of more members. A lot of more members means smoother than single model. Do you think smoothness has any impact to the results?
That's a great question. So this question comes up a lot. Are you getting skill because you're adding more ensembles or because you're adding more models? So there is a clear way to answer that. If the NMME could all generate, say, 80 ensemble members, then we could actually just evaluate and see. In this case, it's really hard to tell. It could go either way. I can't really say for mathematical certainty what the answer is, but my hunch is that it's not due to the ensemble effect. I think the different models are producing different forms of predictability, and so when you combine them, that's why you get an enhancement.
Thanks. Okay, let's move on. Next speaker is Kathy Pegion, who's speaking about a preliminary look at MJO forecast skill in NMME.
Okay, first I'm going to test if I can use the pointer. All right, good. So first I want to recognize Ben Kirtman, who has been kind enough to provide his data from the CCSM4 as it's being run. And it's really, if he wasn't able to provide this data, then there's no multi-model ensemble for looking at NJO skill for this talk. So thank you, Ben. Also, I'd like to recognize the NMME Subseasonal team, and I'll talk a little more about that later. And then I think sometimes we fail to say thank you to EMC and CPC for all the work they do to produce this incredibly rich data set that is available from CFS2 and previously from CFS1. So thank you. It's a great data set, and I look forward to continuing to work with it. Also, thanks to MAPP for funding me and the NMME project, and COLA, who kindly provided some important resources over the last 2.5 weeks that the government was unable to provide. So the first question we might want to ask is, why do we care about the NJO skill? Why am I looking at that in the NMME? And I'll remind you that NMME is a climate testbed project. It's a research to operations focused project, and it's important that we connect the NMME forecast to forecast products produced by CPC. So what we really want to know here in terms of looking at NJO is, can the NMME provide skillful prediction to better inform the forecasters at CPC? And this is an example product from CPC that's in the subseasonal time frame. It's called the Global Tropical Hazards and Benefits Outlook. And this is just an example product taken from the CPC website. It was a forecast issued in September. And it tells us about the increased likelihood of tropical cyclone formation, above or below average rainfall, or above or below average temperatures. And the NJO is really a key factor in producing this product. And so we're hoping that as the NMME moves towards doing subseasonal predictions, that maybe we can help provide some additional information to the GTH forecaster for this product. So the data that I'm using is a very small subset compared to what you previously saw as available for the NMME. And the reason for that is the NMME data that's available right now is for seasonal predictions. That's mostly monthly data, and the forecasts are all initialized once a month for the most part for seasonal prediction. So what I've done here is to cobble together the data available from the CFS2 and the hot off the press, still currently running data from Ben CCSM4 runs. And what I have right now from the CCSM4 is 1982 to 2005, and it's forecast initialized on December 25th, 26th, and 27th. So we'll put those together and call that a 3-member ensemble. And then to compare with, I'm going to use the CFS2 initial conditions from the seasonal reforecast from December 27th, initialized at 0, 6, 12, and 18Z. So we'll call that a 4-member ensemble. So we already have a little bit of a handicap here in the sense that these were all initialized on the same day, whereas these are initialized on different days. So it's possible in making an ensemble that by including old information, we're actually going to degrade the quality of the forecast. Since I'm looking at MJO, the focus will be on the Wheeler-Hendon RMM index, which we heard about this morning, so I'm not going to go into detail about it. And they actually provide that index calculated from NCEP reanalysis and the NOAA interpolated OLR on their website, so I'm using that as the verification. So first I'll ask you to resist the urge to compare models. We're going to focus on the left side on the CCSM4. And there are a lot of lines here, and I want to take the time to really go through and explain why I'm showing you all of these lines. The dashed black lines are the 3 ensemble members from those 3 different initialization dates. It's very easy in the beginning of the forecast to see which one was which. This is the 27th, 26th, 25th. So obviously, in the early part of the forecast, as we would expect, the initial conditions are very important, and by using a day-old forecast or 2-day-old forecast, we're really degrading the skill. But as you get out to about day 14-ish here, they start to come together, and it's not as clear which one is which. So for the weather time scales, not surprisingly, the initial conditions are very important, but as we get to the subseasonal time scale, it's not so clear that it really matters which day. Of course, again, I have a small sample here, so it could simply be that we just have a small number. And so I'll put in a big plug for that this is one of the reasons that we actually really need to do subseasonally initialized experiments for, hindcast experiments for the NMME so that we can really sort these things out. The red line here is the 3-member ensemble mean. And the 2 green lines are ensemble means made from 2 members, with the top one being the most recent 2, and the bottom one being the oldest 2. So you can see that definitely, again, in the beginning of the forecast, it really matters that you have the most recent ensemble members, or the 2 most recent forecasts. And you really lose skill by using older forecasts. Now, if we look at the CFS2, all of those were initialized on the same day. So you can see that they track very closely together in the early part of the forecast. As you go out further, they start to diverge. And then you see that this is the red line here is the ensemble mean of those 4 forecasts. And you can see that the ensemble mean actually is very good. It does very well. And so we have definitely a benefit, certainly in this area, from the ensemble mean. So then the question is, if we put these all together into a multi-model ensemble mean, do we get any benefit from that? So this is all of them together. The black line are CCSM4 and CFS2 together, with the solid line being the 7-member ensemble all combined into one. And the 2 dashed lines here are if you if you make a 6-member ensemble by putting the 2 newest forecast from CCSM with the CFS2 forecast. And this is if you put the two oldest numbers with the CFS2. So I think the important point here is to notice that you do lose something by putting in these older members, but that the multi-model ensemble mean actually does fairly well. It is a good or better than the best model, which is what has been found with seasonal prediction as well. So the quick summary of those results are that the multi-model ensemble is as good or better than the best single model ensemble mean. But then we have the question that can't be answered with the data set we have very well, is the best single model always the best? And that's really one of the benefits of a multi-model, is that it can pick out, it can do this better forecast without having to know at forecast time which model is better. And then the other is that old forecasts can hurt the multi-model skill. And a key question we have to ask, and again, I'll put a plug in for more data, is what is the balance of the number of ensemble members versus the reduction in skill you get from old information? So the key challenges we have in trying to do the subseasonal multi-model ensemble is, as you saw, the data that I have is not initialized frequently enough. So we really need to increase the initialization frequency. But that creates a bit of a problem, as it creates significant increase in the amount of data. It also uses a lot more computing and human resources to produce those forecasts or reforecasts. So this really is the challenge. And then we also have to balance the operational needs with what's feasible given current resources for the research groups participating in the NMME. The problem is really for operational needs to really benefit CPC's products. Ideally, it would be best if these could be run every single day. But most of the research groups that are participating in the NMME simply don't have the human or computing dedicated resources of an operational center and simply can't do that. So the next step in terms of trying to move forward with what can we do with a subseasonal NMME and what benefit might there be in it is this NMME subseasonal experiment. And this is thanks Jim, this is an effort by a group of NMME team members who are interested in the subseasonal problem. And our goal is to demonstrate the potential benefit of a subseasonal NMME in a retrospective context, and to provide a framework for future real-time subseasonal NMME. And this is a list of the participants, and I really appreciate all of these people willing to participate in this, and especially the participating modeling groups who are willing to do the model runs. So what we've done is to set up a very limited scope experiment in order to test the subseasonal NMME by having reforecasts from 1999 to 2012 for a single month where we know the MJO is a big factor, and so we pick November. They'll run for 45 days, and we'll use the every 5th day initialization. Each group can do however many ensemble members they want, but we're encouraging at least 3. And we'll produce a very limited set of variables to at least initially demonstrate, the benefit of NMME for subseasonal. COA has also graciously agreed to manage and archive the data for this experiment. And the one big issue we have is that for connecting to CPC operations is the Global Tropical Hazards product is weekly, but what was feasible for the groups willing to do the model runs was to initialize every 5 days. This brings back the point that I was talking about the old ensemble members and how they contribute to benefit or to not benefit the NMME. So as part of this effort, we'll be testing the impact of the delayed model forecasts to potential skill and trying to understand where that balance is of how many ensemble members to include versus the degradation in skill from old forecasts. Thank you.
Could you say a couple of words about the MGO in CCSM4? Because the difference in forecast skill was quite significant, I think.
No, I can't really say much. The problem is that we have such a limited data set here that it's really hard to look at the events carefully and know how well it's forecast. I did look, there are MJO events that are occurring during this time frame, so we are picking up on MJO. I think part of the issue, and Ben might be able to speak to this, some of it has to do with the initialization. As you could see, this is at day 1, so I don't have a 0-day forecast. I have a day 1 forecast, and you can see that the skill is actually already, kind of lower than the CFS2. So I think it might have to do with the fact that basically, CCSM4 doesn't have its own assimilation system, and whereas CFS2 does. So I think the initial conditions are probably better, at least in terms of how the model responds to them initially.
Other questions? Up, all the way in the back.
I'm following up on Augustine's question. You could actually plot the CFS-V2 day 1 old and day 2 old and check and see whether it looks like CCM4. Because I have a feeling that you're right, it's initialization, and if you don't get it from a data simulation that is actually, consistently running every day, that produces these forecasts. Because I think what we do in operations right now, we have 16 members every day. But to get 40, we just go back 2 days, and you get 32 members. And I don't think they drop like this on the left. So, you could do that. The CFS-V2 is run every day.
Yes.
It has 4 members, so you could actually
plot
that.
And now that I have government resources, I'll be looking at that.
Okay, any other questions? Kathy? Great. Thanks, Kathy. Next speaker is Huug van den Doel, speaking about aspects of land surface hydrology in the NMME.
Okay, let me first acknowledge my co-author, Emily Becker, and the other members of the NMME team. So even though I'm going to talk about land surface, let's first talk SST. So suppose we know since yesterday that the Pacific SST has an impact on temperature and precipitation over North America. What would it take to take advantage of that in a modeling context? Well, you want to make sure that the model has the right mechanisms to do that. And then you want to make sure that we can initialize the model. So if we are in a warm event, you would like that to be reflected in the initial state. We also should thank nature for providing such things as El Nino and La Nina, because you can test models to see whether they are doing the right thing if we think empirically we know what is supposed to happen. So now apply all of this to the land surface. So these are 2 slides that I have in my back pocket. These are all the models that we'll see flying by in a minute. The details do not matter too much, except that there is about a 30-year hindcast for each model. So in the first half of this short presentation, all calculations will be based on a 30-year hindcast. At the end, I go into real time, and that's just single case. So this is the year 1 situation. In year 2, we had these models. And so now the questions are, do we have the mechanisms for feedback back onto the atmosphere in these models? And do we know how to initialize in particular cases? So the way I'm going to study whether the mechanism is there goes back to an old paper in 1993 by Jin Huang and myself, in which we correlated the precipitation in a given month with the temperature in the next month. So this is over the United States, and as you can see, that correlation is negative. In fact, the correlation is negative everywhere, but if you contour only the significant values, you end up with something like the hotspot. This is where the precipitation in the previous month has an impact on the temperature in the next month. So a wet July will lead to a cold August and vice versa. So this is readily available data. And in phase 1 of the NMME, this is basically all we had: temperature, precipitation, and SST. So this is enough to check how this compares in models with observations. So this is how it compares. Maybe we should go back. In this one, we actually had more data, more years, than we are going to have in the NMME years. There's only 30 years. This is more than 50 years. So the observations are also subject to a little bit of change. The observations are given in the dashed line. So the point is that the correlations are all negative throughout the year. So this is the correlation of precip in the leading month and temperature in the next month are negative in the entire year, but they're more negative in the summer, because it's only in the summer that you can change the Bowen ratio. So if you believe this dashed line to be what models should strive for, then you may give the models a pass on having a negative correlation. So indeed, the temperature in the next month is higher when the soil has become wet as a result of rain. But the models are probably overdoing it. They are stronger. They give a higher effect on the temperature in the next month. And so the poster child of the exaggeration is the GFDL model. I don't single it out for any bad intentions, but this is the model that has the strongest impact on the temperature in the next month. Okay, so here you see the list of the models. You can take your pick. The model that comes closest to the observations, at least in the summer, happens to be CFS V2. That has the least impact on the temperature in the next month, and presumably the least impact on changing the evaporation when the soil gets wetter or drier. So this is the same thing again, but now only observations, and this is not just lead 1, these are all the leads. And this is plotted as a function of the target month. So let's say in July, you correlate negatively with the precip in June, still negatively with the precip in May, so there's a little bit of a farther look back, but then it pretty much dies. So there is a short, or maybe 4 or 5 month seasonal window where this happens. There is another little streak that goes here, which I will not discuss, but this may be a case of snow cover. So high precipitation in December somehow correlates negatively with temperature, even at a considerable lead. These are very small correlations, but this is for the entire US aggregated. So how do models compare? So this is the observation now in a smaller display. So you can see that, for instance, the NCAR model has a seasonal window which is a bit longer than in the observations. And GFDL is kind of very strong, but very focused in just the canonical summer. And here is the CFS. I have all the models, but I'm not going to discuss all that. And there's also the issue of spatial maps, so now it's evaluated at each point separately. And so these are the observations that do look a bit different from the one I showed in the beginning, in part because this is 30 years only. And this is combining now all the months in the summer, so it's the correlation of precip in April with temperature in May, precip in May with temperature in June, so to get a little bit more of a sample. So it's basically negative everywhere, but small. And you can see that the models are overdoing it a little bit, the CFS models least so, and then as you go down this list, I guess GFDL is the one that overdoes it the most. But in general, almost all models have this mechanism a bit stronger than we think we detect from observations. You can do a lot more with the model data than with the observed data. And the reason is not only that there are many ensemble members, the previous calculations were done with just one ensemble member, not with the ensemble mean. But in this case, what I'm showing is that if you correlate the precip and the temperature 1 month apart, but the lead in the dynamical model is lead 1 for the precip and lead 2 for the temperature, you can do the same calculations for lead 3 for the precip and lead 4 for temperature. So as you go deeper into the forecast, we see that this diagram doesn't change very much. So the model is quite comfortable with doing its own thing almost immediately. And this is particularly remarkable because some of these models do not initialize their soil moisture. So they set up the right pattern, I guess, as a result of the rainfall in the first month, which I had not expected. Okay, so this was all based on the hindcasts. Now we are going to look at the real-time experience, and we can do that because soil moisture was added as one of the 5 variables. And so this thing has come out in real time only since a few months. So now we can look at a little bit more. It's a little embarrassing, but we apparently didn't think of agreeing on the units for this quantity, so you'll see both percent and millimeters in a minute. The real-time display of this started in May, I believe. Emily will say a lot more about what started when. The initial conditions is about May the 1st. Some models are a few days earlier. CFS is all the way up to May 7th, but about that. To the extent that I'm talking about forecast, they are very early in these run in June. We're going to borrow the color coding from the CPC leaky bucket. So this happens to be the distribution of soil moisture in the spring. And this is not a La Nina event or an El Nino event, but it is unusually strong. There was a lot of concern of what might happen in the summer that would follow this. But aside from that, this is a pretty unusual and very clear-cut pattern of dry in the west and wet in the east. You're not going to see this too often. It's usually far more broken up. So this is now the quote-unquote observation. I will show another observation in a minute to verify that this is not total nonsense. So this is the observation. And with the same color coding to the extent possible, we have here 6 models which are running at the moment in the NMME. So some are in millimeters, some are in percent, but it's all anomalies. So the only model that looks anything like the initial observation is NASA. And I should say that NASA discovered a problem with the soil model or the initialization about 6 months before this moment. And they worked very, very hard to do something, and they apparently achieved that goal. GFDL and NCAR do not initialize their model, so you can hardly blame them for the fact that these maps don't look like that one. That's a given. Everybody is free to design these experiments any which way they want. That's not part of the protocol. So we have only NASA. The Canadian models have technical problems, and those were also discovered before I made these plots. And Bertrand will talk about those technical problems, but you will probably agree that these Canadian early states in the model runs also don't show a whole lot of similarity with the very strong and well-defined initial state. And of course, I'm most disappointed that the CFS V2 doesn't look like much. And so this goes back to some of the things that Paul Durmeyer was telling us this morning. The CFS-R is much too wet in the west of the U.S. And that's elaborated on here. So this is again with the leaky bucket, and this happens to be for the month of May. And this is the same thing based on the NOAA land model in the offline calculation. And so these are 2 estimates of reality that have quite a bit in common: dry in the west and wet in the east. So the color coding between these 2 is not coordinated, as you can see. But the CFS-R, which is really the initial state for the CFS V2 run, is much wetter in the west than nature is, according to eyewitness observations and these 2 estimates. So that's a little disappointing. Okay, the conclusions. Most models appear to feed back onto surface air temperature via evaporation by changing the Boeing ratio, etc., by the correct sign and the correct seasonality, but they are somewhat stronger than nature, and GFDL is probably way too strong. It produces even very high positive persistence in the precipitation anomaly. So every drop is savored and used over and over again. That's something you can't find in nature. So almost all models, and the CFS V2 especially, have major problems initializing soil moisture anomalies. So the thing is anomaly here. Go back to the ocean. I mean, how do we judge whether the ocean initial state is right? Well, when there's a warm event, you like to see warm anomalies in the SST field. So we seem to be missing that for the most part. Only NASA was pretty decent. So if you look at these two factors, one may be too strong, and we are not too successful at this point initializing a strong event. We have a way to go to take advantage of any surface hydrology-related predictability. So in a way, this is good news, because we have something to work on, and we have something to look forward to in terms of harvesting skill. And by the way, there is no ENSO as a test case in hydrology, and I think that's one of the things that holds it back. You can do experiments, but the verification is not as straightforward as on a outspoken case like ENSO, where we pretend we know what the answer should be in the forecast. Thank you.
Thank you. Time for one or two questions.
Yeah, I think suppose this model also all this greenhouse gas change with time.
Some of them.
Yeah, all of them. I think for GFDL model, for example, they have a very large negative correlation. I think it looks like they're very dry. So that maybe have a large warm tendency. That cause have a large negative correlation. So I think probably you should fill out the low fluctuation, just focus on the short time fluctuation, then make compare.
Well, the anomalies inside each model are relative to their own climatology, but it is true that GFDL, in addition to being too warm, also has a huge upward trend. They are forced not only by CO2 increase, but by some scenarios for the aerosol on the troposphere. So yeah, there is a low frequency component to these negative correlation, not only in models incidentally, but also in the observations. So.
Any other questions for Huug? Okay, thanks. Next speaker is Bertrand Denis, who will tell us about soil moisture biases and their correction in CanSIPS operational forecasts. Can we have the next talk, please?
So good afternoon. First of all, I would like to acknowledge the work of my colleague in the Canadian Centre for Climate Modeling and Analysis, Bill Merrifield, Kharin Scinocca, and Woo-Sung Lee, who is present today. Okay, so a brief introduction to the Canadian Seasonal to Interannual Prediction System, CanSIPS. It's been developed at CCCMA on the West Coast, and it's been implemented in the Canadian Meteorological Center in Montreal. It's operational since December 2011. It's a multi-model ensemble system. It has two models, the CanSIM3 and CanSIM4, 10 members each for a total of 20 members. The forecasts are initialized every month. The Hindcasts period is 91 to 2010, which is pretty standard. Our forecasts contribute to the NMME, the WMO, the APCC, and also the IRI ENSO plumes. and the forecast range is 12 months. So if you go on the NMME web page, you'll see CMC1, CMC2. These are the two models, 10 members each. Okay, let's talk first about the CanSIPS initialization in general. What we do is, for each of the members, we have started more than 30 years ago with initial conditions slightly different. But we do assimilate global analysis, not observation directly, but global analysis are assimilated in each GCMs, each member. We do that 6 hours after 6 hours. And, and anytime we can start a forecast from those initial conditions. So each members are slightly different for their initial conditions, but are very close to the real observation. So it's burst initialization. It's not time lag, which is good for zero-time late forecast. Now, a few words about the land initializations. Well, as I said, for the atmosphere, there is we assimilate global analysis, so winds and temperature, moisture, using incremental analysis update, kind of a sophisticated nudging. But for land, there is no direct assimilation. It's indirect. In fact, soil moisture, snow are not directly constrained. Their states are determined by the model response to previously assimilated weather systems from the 3D global analysis. Now, as you'll see, the problem that we have faced came from the fact that we used different data sources for the Hindcasts, for the assimilation cycles, than in real-time operation. So for the 3D atmospheric field, we use the ECMWF data. But in operation, we use our own CMC global analysis. We use also SST. We nudge the SST during the assimilation cycle. For the Hindcast, it was the monthly INCEPT and also the weekly INCEPT OISST. But in real time, we have the daily CMC SST analysis that we use. Same thing for our CIs. For the 3D ocean temperature, I mean the deep temperature, they are just assimilated when we do the forecast, not in the assimilation cycle. We leave the ocean model by itself. Okay, so as you saw, the sources of the data for the Hindcast and the forecast for the assimilation cycles are different. So we saw a problem. If you look at what I'm showing here is the volume fraction of the soil moisture. We have the two models here, okay? So previously to 2010, the assimilation cycle had the ECMWF data. But after that, when we started to assimilate the CMC atmospheric data, we saw a drop in the soil moisture in the two models. But we continue also on the side to assimilate the ERA data, and we saw that there was no drift. So the drift happened because we switched the global analysis. Seems like the CMC analysis has less moisture in it, probably, compared to the ERA data. So this is global, but this happened also over Canada and the US. It's almost everywhere. So we were drifting a lot. So what does it mean is, okay, if you look at the upper panels only, these are the forecast, the soil moisture anomaly forecast. There's many curves on that. all the members are there, but the most important curve to look at is the black one here. This is a 12-month forecast. When we use so in 2010, when we used the ERA data in the assimilation cycle, it was pretty stable. When we use the CMC, the initial conditions that came from the assimilation cycle were very dry, but the model was able to come back during the forecast. Okay, that was there in 2011 and 2012. And if you look at the lower panels, these are the zero-time link, the soil moisture anomaly forecast for July. You can see that with the ERA data and the assimilation cycles, we get dry area, wet area. But with the CMC, it was a lot more drier and almost everywhere. So the solution was to implement a bias correction. The steps that we have used to do it is, as you saw, we extended the ERA-based assimilation cycle up to mid-2012. From these, we saved the 6-hourly soil moisture time series starting from 2012. The third step, we repeat the CMC-based assimilation runs, but we assimilated the soil moisture from the step 2. So it is a relaxation using the data from the right assimilation cycle that has the ERA. In step 4, we saved these. We fit an annual cycle using 3 or 4 Fourier mode. Okay, keep that as a constant, but that can vary from day to day with an annual cycle. So that is our correction term for each grid point. So we had a correction term computed. So we repeated, we came back, we restart the assimilation cycle, but including this term with the CMC-based global analysis. And we hoped that those drifts will go away. And you'll see that that worked. So what I'm showing you here is for Canada, the mean soil moisture anomaly in July. So this is the first, just a 1-month forecast for July. It was really in July the worst cases, okay? So that's a 12-month forecast. As I said, because of the very dry initial conditions, the forecast started very dry, but was able to come back a bit. With the ERA, as you know, it was right. When we implemented the bias correction, well, the initial conditions that was too dry was very similar to the ERA, and the model continued correct. So the correction was implemented operationally for the June zero-time lead forecast. So it is very recent. If you go on the NMME webpage, you have to look to the July forecast because there's a 1-month lead time. And you will be able to see the difference in the precipitation and also the temperature, which is lower. So this is an example. With without the correction, the problem was not only seen in the soil moisture, but also in the precipitation. There was a big deficit compared to the ERA-based assimilation. So when we implemented the correction, most of the differences disappeared. And there was a big effect also on the 2-meter temperature. So this is a July 2012 temperature anomaly forecast. The contours are difficult to see, but The verification shows up to 3 degrees of anomaly for that month. Okay. Without the bias correction, we see that the temperature, the 3-degree contour is larger, it's too much. When we did the bias correction, it reduces a bit the area, and it was very close to what we expected using the area initializations. So in summary, change from the area reanalysis for atmospheric oscillation in the Hindcasts to CMC analysis in operational forecast led to accumulating moisture deficit that took just a few months. This has been fixed using a bias correction procedure similar to Kharin Scinocca. The soil moisture in the Hindcasts is okay. When we changed it, when we switched to CMC global analysis, that we had a problem. And we did that in June 2013. Okay? But the soil moisture in the operational forecast that has been sent to NMME, for example, or PCCWMO, had a problem between November 2011 and May 2013. And that's it.
Thank you. Questions for Bertrand?
Bertrand, the point that you brought up with the soil moisture is what Huug brought up also in the adjustment there from the soil moisture and the CFS. And so I just wanted to bring up a point in the data simulation we've done here in the GSI, which we're applying only to the regional model right now, but doing basically using the analysis increments of the low level temperature and moisture, using kind of assuming a Bowen ratio error that would be there to adjust the soil moisture on an ongoing basis. So we haven't tried this yet in any way with global models, but it could be another way to add on to the adjustment that you did here with the RA analysis. So something to consider. Maybe you already have something like that, but I didn't see that there. So it'd be something more of an adaptive way that could be applied in a global analysis from the low-level temperature and moisture increments.
Bertrand, you mean right now you already identified the problem from the model, so you don't need a bias correction anymore?
Well, the problem is not necessarily the model. It's more the change in the global atmospheric analysis that was assimilated during. It's really that. I mean, maybe ECMWF has too much moisture. I don't know if somebody knows that. I'm not sure, but that could be the case. But we did the Hindcasts with that. So when you do a forecast of anomaly, your climatology, if it's too warm, too wet, you have to live with it.
Last question, Suru.
This problem should be in all of the variables. I mean, you're going from one data simulation system to another for your initial states. And unless the Canadian data simulation system is similar to ERA interim, you're going to see this problem in pretty much everything.
Well, we didn't see in everything, but what I can tell you, and probably you have also the same issues, is each time there's something changing in the environment, well, it could be the resolution of the reanalysis, or in our case, we nudge with the SST. The SST has been changed with a different assimilation. CIs also, we're going to have a new CIS analysis that will be used to nudge. Every time there's something in the environment, the operational environment that we use to assimilate in our assimilation cycle, we need to test again. And we do statistical tests on temperature, and often what happens is, because the scale is often not very high, even if there are changes that could be bad, but there's already a lot of noise. So when you do the statistical analysis, verification, maybe there are differences, but in a way, there's a lot of noise in a way. Maybe over the tropics is different, but over Canada...
And that means that every time in operations you make a change to your operational data assimilation system, you have to keep testing and testing again and again to make sure that the anomalies are on track, correct?
Exactly. We're going to implement a new global analysis based on hybrid ensemble Kalman filter within a year at 15-kilometer resolution. Well, we'll see. We'll have to redo what we've done just to be sure that the bias correction term is still right. If not, we'll have to recompute it, and it's a big job to maintain an operational system like that. I'm sure you're aware of that.
Did you know that, Sue? Okay, I think I'm going to cut it off there. There's a break coming up. Will be a chance to discuss further. Thank you. Next speaker is Emily Becker, who will talk about the North American Multi-Model Ensemble verification of real-time monthly mean forecasts.
Okay. I, too, completely changed my title. NMME Year 2, verification of real-time monthly mean forecasts. That's the only part. I'm actually going to give a little advertisement in the beginning and then cover some of what we did in Year 2 of NMME. Thank my co-conspirators here, Huug, Qin Zhang, and Malachias, who is at EMC. Okay. So Arun mentioned this yesterday. There's a meeting in February, the International Conference on Subseasonal to Seasonal Prediction. I attended the seasonal to decadal prediction meeting back in the spring. This is a similar project. It should be very interesting, even if you just absolutely love this room and really want to spend another week in it. You can submit an abstract. I have don't write that down. There are flyers outside on the registration table. So if you're interested, please come and take a look. All right. So Year 2, the NMME just celebrated its birthday back in August. Yes, this is my 2-year-old niece at her birthday. New operational configuration. Now we have 6 models instead of 7. We have additional variables. We have debuted experimental probability forecasts and a new real-time verification webpage that you can look at. You've seen this a few times. Just to recap, Year 1, we had 7 models, including CFS version 1 and 2 models from IRI. Those have dropped out, but we have included now 2 models from CMC, which Bertrand was just talking about. And we, just rule of thumb, we tend to call the models by their center. So for example, despite these being CanSIPS 3 and 4, we call them CMC 1 and 2. So just so you know which models I'm talking about later. All right, our additional variables. Huug talked about a couple of these live since April 2013, in fact. Initial conditions, so the first forecast was from May 2013. We have 200 millibar heights. We have Tmax, Tmin, and soil moisture and runoff forecasts. There's still some kinks being worked out for soil moisture and runoff. And these are available from a link on the homepage that says additional variables. It's just a preview of them. As Jin covered earlier, there are going to be a lot more variables in Phase 2 that will be released. So this is a preview of them. And yeah. Okay. Also, new, we have experimental probability forecasts. The official forecasts are, thus far, all anomaly forecasts, deterministic forecasts. So these, which went live in November of 2013, show just simple tercile probabilities for above normal, below normal, or near normal. The tercile limits are determined for each model using the Hindcasts for that model. And then the NMME probability shows the percent of each of the 79 total ensemble members that fall into each category, just to give the forecasters an idea of forecast confidence. And we have above, below, and neutral indicated by the colors here. Also new, we have real-time verification. This is a slightly difficult to understand web page, but it's a temporary product. Right now, I'll show you the expanded version of it. So this huge grid shows you have your initial conditions, all the forecasts from the start in August 2011 through August 2013. Haven't updated the forecast past that yet. But you can, for both monthly mean and for seasonal, you can scan across to find which period you're looking for the forecast for, and say you want from the January 2013 initial conditions the forecast for March, April, May, which is lead 2. You can select that. Actually, this isn't that. This is a different forecast. But when you click that, you get this web page, which repeats the, it takes the forecast for that period, shows you the observed value, and then also shows you these scores here for that individual forecast. So I will explain what those bars are in a minute. But this is the, you can see these for each forecast. Say you're curious about that very high temperature that we had in March of 2012, see how well that was forecast by the NMME. You could take a look here. So what are those bars for the real-time verification? We, year one, let me back up just for a sec here. Year one covers forecasts from September, October, November through August, September, October of 2012. So that's a full verification period. We do not have a full verification period yet for year 2. But what I'm going to show now is just the seasonal. You can take a look at the monthly if you like yourself. And so what we have here is it's a simple pattern correlation between the forecast, the observations. We take the area average for each model and then for the multi-model mean together. And so you get an indication roughly of how good the pattern correlation was. I've only done North America, Southeast Asia, and Europe. We'll get to the rest of you later. So, all right, some results for these. Year 1, as I said, is a different ensemble because we've got the 7 models, and then we have 6 in year 2. So anyway, year 1, this is for temperature, and then year 2, we've got temperature, and then P rate down here. Year 1, we had nice strong scores. This is the average over the entire year of the first 3 seasons from each lead. So you've got a total of 36 seasons being averaged in here from 12 initial conditions. So these, I actually had to stretch it a little bit because the scores from year 1 were quite high. There were several very strong extremes in that year, the first half of 2012 in particular, and the NMME actually did pick those up quite nicely. We suffered a bit in year 2 from some less clear signals. But, and even during P rate, which you would expect to be low because we just expect it to be low, we did somewhat well for the first year and still had positive scores for the second year. I realize there's not exactly a whole lot of statistical significance just looking at small samples like this for real-time verification, but there are some patterns that begin to emerge, including the fact that the green bar, which is the NMME bar, the 7 model or 6 model ensemble, is not always the highest, but it is almost always among the highest, whereas the other models you see a lot of variation. Going to North America as a whole, we see that there were some more difficulties here. A lot of variation, but the overall NMME score was higher. And then with the two Canadian models in the next year, we've got slightly lower scores, but still positive. And for P-rate, yes. So, okay. Southeast Asia, temperature scores are high. Here, well, not high. I realize I'm talking about 0.2. But anyway, they're positive, and we still have our green bar is the strongest, indicating that the NMME is performing. P-rate, yeah, not good, don't look. Okay. Over Europe, more stronger temperature, weaker precip, which is not a surprise either. And just these are just boxes that I made, the latitude, longitude boundaries. I think Europe goes to 60 east, and for Southeast Asia, it's 55 north, down to about 5 north. So it's China, most of China and India, so it's Asia, Southeast Asia. All right, this is a bit of apples and pears because this is from the Hindcasts, but having talked about the forecast for a while, I wanted to give a little context maybe so we could see what we might have expected to get. This is from, as I said, the 30-year Hindcast, and it's from a configuration that we have never had live. It has CFS1 and the Canadian models, but not the IRI models. However, this is just for the multi-model ensemble. Each of these winter, spring, summer, fall for the northern hemisphere. And this is your anomaly correlation times 100, again, as the bar chart showed, so that you can get some idea that temperature scores, we do see some skill above 0.3 in a lot of areas. 0.3 is the limit that we currently use for the skill maps. Thank you. However, when you go to look at precip, we are not particularly surprised that our scores for the active real-time were low because there's very, very little skill here. There is, however, more over North America. And here's your little glimmer of hope. Again, another Hindcast study. This is just something I grabbed from another project, but looking at predictability, so the potential predictability from the perfect model assumption. So you take one member of the model and you call that your verification, and then you take the remaining members, average them together, and call that your ensemble mean. And in theory, the model predicts itself. Model predicting itself will give you an idea of the potential predictability. And here we have the forecast skill again. And this is just for the Southeast Asia area, but we do see that while the forecast skill itself is very low, there is perhaps somewhat a glimmer of hope that maybe with some further improvements we will have a chance to increase that skill a little bit. We'll see. Particularly, the colors here are for the seasons. This has each model the first season. So blue is winter, so that implies that perhaps during winter we could see some better luck. Okay, year 2 recap. We had new variables, new analyses added to the web. Take a look at the web page. If you have any questions, feel free to email me. And yes, our real-time verification, we find that while we weren't blasting the lid off of the scores, the NMME forecast, the MME rather, is the highest, not always the highest, but it's among the highest. And for our year 3 preview, we are going to have a new web page. We're very excited about this. It'll bring us into the 21st century instead of my circa 1998 web programming skills. I'd like to do some verification of the probability forecast, verification of sea surface temperature, add that in, and of course phase 2 as Jin went over earlier. I'm going to leave you with a picture of what the government shutdown looked like for me, which was trying to avoid my cat as she helped me work. So.
Thank you. Questions for Emily? Perfect talk. Your skill score is 1.0. Okay. Next speaker is Qin Zhang, who is going to tell us about the upward temperature trend from 1982 to the present in the NMME Hindcasts.
Okay. Enough close? Okay. I'm going to talk of the upward temperature trend in the NMME Hindcast. As all of you know, the NMME Hindcast designed to the bias correction for the seasonal prediction. So it is rather than to investment the climate change. However, it is a little secret for the forecast. The scales of seasonal temperature prediction during the period of 1982 to present, it's strongly upon the trend of the temperature. So that's why one of the CPC's seasonal prediction tool is called OCN. That's Optical Climate Normals. That's very useful for the seasonal forecast. So the seasonal prediction and the climate change are mixed. We can use the NMME Hindcast to look at the performance of the model of the climate change, as long as the Hindcast is long enough. But unlike the free run of the simulation of the model, the forecaster of the model has the initialization in the beginning, in the initial condition for the SST. So even if there are no CO2 increase, such as the CFS version 1, they still have the upward trend for the SST and 2-meter temperature. So now we have the question, do we need an increase in CO2 to get the SST forecast correct? And is the correct SST prediction enough to produce an upward temperature trend over the land? In other words, we may ask it, do we need increase in CO2 in the seasonal forecast model? I will skip these two model description of the NMME HF model. I give you these results of SS trend for the average over the global ocean. The black line is the observation of SST for OISST data. And you can see the climate change is not the straight line. So we can just estimate of the climate change as the straight line representative of the global warming. Of course, this estimate related to the beginning of the year and the end of the year. The color lines are all of the each model's average over the ocean of SST. You can see all of the model have the upward trend of SST. This is only for 1 month lead forecast. But most of the model have the weak trend than observation. Here is the 2-meter temperature trend for the average for global land. We have two observations at here. One is the CFSR in solid black line, and another is called GHCN, the temperature, 2-meter temperature only land. That's dashed black line. Even though these two values not exactly the same, but their trend is quite parallel. Look at the color lines. All of the models have the upward trend of the temperature except one model. Did you find it? Here is the yellow line of this model. This model have no trend on the average on the global land, but it has the trend on the over the ocean average. Now, to avoid confuse, please notice these few points. Here we will discuss the SST versus 2-meter temperature issues over the ocean and the land. Some models have been used for IPCC before. And also some models not only have the CO2 increase and also have the prescribed aerosols, for example, the GFDR's model. And the study we choose, the period, is from 1983 to 2010 for the target months. For the target months, leader 1 to 8 forecast. And today I only show the annual mean temperature for model ensemble mean. In order to qualify this comparison, we calculate the upward trend translated to the unit of degree per 30 years. So here give the number of these all models for 30 years change of the temperature in Celsius degree. The first two columns are observation. You can find over the ocean, they are very close. It's nearly half-degree warming for 30 years. For the land, they are nearly 1 degree warm over the land. Look at the models. Here model, it's most of model, it's a weak warm trend than observation. Only the CFS version 2 have slight higher trend over the ocean. We will later see it's what caused this higher. And over the land, you can see all of the model have maybe CFS version 2 is between of these two observations, but other models have a weak trend. Maybe you notice that the last model, the trend is nearly 0. That's Hindcasts model switch off the GHG increase for the NMME runs. So that's give a chance to see if they need to increase the ocean along. This give us chance to look at if only have a simulation of the SST, maybe not enough to drive the warm trend over the land. Now we comparison with the 30 years trend with the different leading time. The up tables is exactly the same as the last, just showing the slides. The low, this one is the leading 8 months forecast of the NMME forecast. You can find most models have the equal or weak trend at leader 8. Only the GFDR's model here it has a strong trend with the leading time. And also you can see the CFS version 2 getting weak with the leading time, but it is big improve for the CFS version 1. Here I give you the results of comparison of CFS version 1 and version 2. CFS version 1 is fixed CO2 at 1988 value. So the trend of the CFS version 1 is pretty weak compared observation, and also decayed very quickly. And CFS version 2 fix this problem. It has the CO2 increase with the time. It's much better, much improved with the CFS version 2. Here, I show you some special map for the trend. You can compare with this observation. This followed by 5 models for the leading 1 month SST forecast. You can see all of these models catch the main patterns of observation, same as observation. For example, the warm trend over the West Pacific of the equatorial region here, and also North Atlantic region. And two of models, CFS version 2 and the NASA's model, catch the warm trend over the Indian Ocean very well. However, the CFS version 2 has 2 warm trends over the East Pacific along the equator. That's why the ocean, the trend over the ocean is higher than observation of this model. And also CFS version 2 have a pretty warm, and NASA's same as that one on the North Pole region, but it's cold on the South Pole region. Next is the difference of the 2-meter temperature for this period. These have 2 observations. Maybe you can concentrate on the contour lengths. You can see the pattern is quite similar for most of the model. Catch the warm trend over the European and Asia continent and North Africa continent, as well as the South Northern America continent. For detail, we brought these figures to look at the North America. You can find the warm pattern for every model. It's quite similar as the observation, but the center location are different over there. And also, maybe you notice the CFS version 2 have pretty weak the warm trend over the northwest United States, and but the patterns over the Alaska is the best model. So summary, the most models have weak uptrend than observation, both over the land and over ocean. In spite of the ocean data assimilation, the 1-month lead forecast still too weak of the SST. One model, it turned off the CO2 increase, has temperature increase over the ocean, but not over the land. And the special pattern, the trend of the 2-meter temperature and the SST are somewhat very similar as the observation. So that's all. Thanks.
Thank you. Questions for Qin? You also get a perfect score. Thank you. Okay, our next speaker, Suru Saha, speaking on gauging systematic errors of NMME models.
Hi. Well, we were shut down for 2.5 weeks, and I'm the perfect procrastinator. I decided a long time ago I was going to do it in the last week. And obviously I didn't have any access to any computers, so I had to put this together in 3 days. So you'll have to forgive me if it's way too short, and I plan to do a lot more, but this is all I have. So we're going to gauge systematic errors in the NMME models, and this is a husband and wife team effort, so Huug's in there. And I need to acknowledge Qin, who really helped with the data and stuff. So even when the predictability of models can't be verified, for instance, you take a weather forecast at day 18, it has no meaning, or a forecast 13 years from now. They can still be validated in terms of the climate of the system, the model that you're using. And so how well do state-of-the-art models reproduce the observed climate at long leads? So climate is a zero level of skill. I mean, that's the thing you're supposed to know according to any verification system. So we really shouldn't get any brownie points for doing the obvious. But how easy or how hard is it to do the climate? And how close are we going to come to observations? So we know that intuitively, the smaller the systematic error, the better the model is. However, we don't have sufficient hindcasts or retrospective forecasts to actually determine whether the next NWP model is going to be better than the previous one. Because in an operational center, we are chasing timelines. We have to get this done by this certain date. And so even for version 2, when we developed version 2, the systematic error improvement relative to version 1 was not a given. We did a few, hindcasts here and there. But it was pure faith we went on, and when we completed the set of hindcasts, they were only made after a new model configuration was frozen in time. You couldn't go back and redo all of the hindcasts. So this is the thing that we have with operational models. We can only we really are in the dark, especially with seasonal models, of how good this is going to be. And so it is kind of interesting or kind of good and bad for me to sit in the back and see the baby we put out as version 2. Some people love it, some people hate it. But when we actually put it out, we had no idea of all of the research that is being done now to say how good it was or how bad it was. And that's just the way operation centers, models are run. So now NMME provides another opportunity for comparing this in different models. So now the next time around, when we have version 3, we not only have the older version 2, we'll have a whole set of NMME models to compare against. So that's a good thing. All right, so definitions and data. The variables and areas we studied were just the only things we had in phase 1, which was a global SST, precipitation, and I concentrated on the land-only 2-meter temperatures. The validation is the Global Historical Climate Network, CAMS data set for 2-meter temperatures, the CMAPP for precipitation, and the quarter-degree OI SST for SST, which was the input to CFSR. And it's a 28-year data set. And we brought all of the models to a common 1-degree grid. And this is, you've seen this a lot, but this has a little bit more information. V1 is at the top, which is now extinct. We have version 2, GFDL, the 2 Canadian models, NCAR and NASA. And as you can see from the members, you'll see that CFS V2 has the maximum number of members. And so there could be an advantage. I'm not sure when people do their means, whether they take the same number of members or they just take, what I did is I took whatever was available. And then, and again, CFS V2 has an advantage of being also one of the highest resolution models, and also it comes from initial states that are 28 kilometers. That's
makes a big difference, especially to the short-term forecast, where you have very good initial states at very high resolutions running data simulation systems. There are no perturbations in the Hindcasts. We don't perturb any members. They come straightly and directly from the data simulation system. Okay, now this is an ad for the paper. The early online release is there, available on the Journal of Climate for the, took a long time coming out, but it is coming out. All right, so here we have the annual mean systematic error over this period, and I've chosen lead 3, and I'll explain to you later why I chose lead 3. What you have here, this is, I put the paper here because this is one of the diagrams in the paper. V1 on the left, V2 on the right. You have 2 meter temperature on the top, precip in the middle, and SST on the bottom. And what I'm showing here are just the systematic error. This is not really skill or anomaly correlation. This is just the climate of these systems. And at the top, you have 2 numbers. This is the aggregate, global aggregate. One is the bias, the mean, and the RMS is the difference between the 2 climatologies, observed minus the model. And as you can see, just from a straight difference, the patterns are very similar, but you can see that there's a real reduction in the error for version 2, both for 2 meter temperature and precip. I can understand this because V1, the patterns look so different between V1 and V2 for the SST. We do have MOM 3 here, and you have MOM 4 here. So, I mean, they're very different. But if you look at the RMS, in every case, there is a reduction. So, you know, version 2 was better than version 1. But remember, when we went operational, when we started the Hindcasts, we didn't have any of this. We didn't have 1982 to 2009 present with us. All we had was a few Hindcasts here and there. So it was kind of nice that this came out after the entire Hindcasts were done. So I wanted to tell you why I picked lead 3. What you have here is the lead versus the bias in 2 meter temperature and RMS, P rate, and SST. And if you look at the bias, you can see that it increases very slowly with lead. And the RMS as well is a very slow growth. And in precipitation, however, it saturates right at the start. There is no, you know, it's so bad, you're at your predictability limit by lead 1. And then in the SST, again, there's a very slow growth in the RMS and in the bias. So you can see that the model is very quickly in a stable regime for the systematic error. And this is true really for all models, not just for CFS V1 or V2. And that's why I picked lead 3, because, you know, it's in the middle, it's representative. And there's only a very small further development of the error later on. And in precip, there's absolutely no development. And that's what I've here. And there's another part, is that, for instance, the version 2 upper ocean cools in the long CMIP runs. We've made 4 very long CMIP runs. One of them is 100 years. And if you look at it, you'll see that the upper ocean cools very slightly for the first 20 years. So even though we are increasing the CO2, there's this intrinsic error in the system that it'll cool, and then only it's after 20 years that the warming starts to take place. And so, of course, if you really want to look at the global warming, you need to do a control run, which we never did, with no CO2 increase. And the difference will then show you how much of the global warming is really occurring, but that's another talk. So now we look at all of the NMME members. And here is version 2, GFDL, NASA, NCAR, and the 2 Canadian models. And what I wanted to show you here is that they're all very different. And if you look just generally, you see there's more blue than red, so there's more of a cold bias. And if you look at the 2 Canadian models, you'll see they're just distinctively very different. But when you put all of this together, and you look at the RMS, and you look at the ensemble mean RMS, and you actually can see this is the mean. Now, I'd like to have a model like this. Look at it. I mean, it just cleaned up everything so nicely. You look at the individual models, and you look at the NMME. Now, the whole point is to make a model like that for version 3. Okay. So this is SST again. Each model has its own signature, its own biases, and when you look at the NMME, it pretty much cleans up everything. So this is what I'm saying. When Tim talked about complementary skill, I really believe it, because you see here that there is error all over the place in all of the models, but when you put a straight average together, you virtually clean it all up. And that's because there's complementary skill from all of these models coming in together. And here we have precipitation, and this is really ugly. But when you put it all together, you get this. So this is just the climate. This is not skill. This is just the biases of all of these models and how you can make it better. So here are the conclusions. So none of the 6 global coupled ocean models have absurdly large systematic errors. So one of the reasons this really works is none of these models are outliers. They're all good models. Basically, they're all good models. Now, if you have one really bad model, you wouldn't see this. So I think for any NMME to work, you must have some level of basic skill in all of the models. You cannot have an outlier that is completely bad. And so in this case, we're lucky. We've got 6 models that are relatively good models, and so when you put them together, none of them have absurdly large systematic errors. They're reasonable, comparable in magnitude, and there's not really, you can't pick any winners or losers because no model is best for everything. CFS V2 may be good for 2-meter temperatures. GFDL is probably very good for precip. I don't know, but nobody's best, and that's the whole thing about complementary skill. But the greater tropical Pacific region is still difficult to model for all of the 3 variables, and I think this is where version 3 or the next versions of these models have to concentrate on, is how do you get better forecasts for the tropical Pacific region, which is very important, and especially in precipitation. And so the annual mean is smaller in the NMME than in most or all of the constituent models, and there's obviously some minimization of the error by taking a straight average of all these different models. But remember, if the patterns were all the same, then the NMME wouldn't be showing anything different. It would just show the pattern. But in this case, there is a cleanup of the error. And I haven't shown this, but the systematic error in an individual month is much larger, of course, than the annual mean. And eventually, all of these maps will be put on the web, so you could possibly just, on a click, just go and look at the biases in any of these models for these variables. And I'm trying to address one before we all go out for the tea break, is that people talked about the difference in the climatology in version 2 between the earlier period and the later period. And I just wanted to give you an idea of what these differences were. So on the left, you have the 1982 to 1998, and then 1999 to 2009. So the 1998, the end of 1998, we assimilated the ATOPS data, the ANSU-A data, which really changed the whole precipitation patterns in the tropics. But if you look at the actual patterns for 2-meter temperature, precip, and SST, you don't, I mean, there are differences in the tropics, yes, but if you look at the extratropics, you don't see very much difference. So we have put this in our website, saying that if you use anything in the tropical, and really it's only in the equatorial area, then try to separate the climatologies when you're doing any skill estimates or using it for bias correction. But for like 2-meter temperature and precip over the US, please just use the whole data set. You do not see a difference in climatology away from the tropics. So I just wanted to let you know about this. Thank you.
Thank you. Questions for Suru?
So this is very interesting. I wish you had more time so you can show us the biases in individual months. You suggest maybe in July and January the biases are larger than other months. I wonder if the July the biases are common among the models, so they may not cancel out with each other. Yeah. That may be the highlight. Well,
I said blame the government shutdown. I was planning to do all of that. Just didn't have any time. But they will be on the web soon. I'm sure Emily will take my maps and put them there, right, Emily?
Can I ask a question? The rosy picture that you painted, which is nice, about the RMS being canceling out and looks completely clean, does not, of course, quite translate into the correlation measure, which we saw earlier, where the improvement is only marginally better. So,
well, as I said, for modelers, and I come from EMC, I'm not CPC.
I agree.
For modelers, all we can do is address the systematic errors. There's no way to do random errors because by definition, they're random. So when we try to get a new model together, we look at the systematic errors and try to minimize them. And that's all really one can do. And hopefully, getting a better mean state will evolve to get better anomalies.
Agreed.
Okay. I think we'll quit there, take our break. Before we do, I'd like to thank all the speakers from our longest session. Thank you all very much. And thanks to all for also keeping your time, because now we have 20 minutes for a break.